So now we're switching gears a bit. We're going to talk about certified solving, proof logging for branch and bound MaxSAT, taught by Dieter Vandesande. Without further ado, please.
Yes, hello everyone. So this is joint work with Jordi, Chumin, and Bert. And I guess we're all here because we like to work at combinatorial search and optimization. And we are pretty good at it already. I mean, in the last few decades, we have seen a big revolution in the efficiency of these kind of solvers. And we can nowadays solve very difficult problems in a reasonable time. But the dirty little secret is that these solvers are sometimes incorrect. And of course, I believe that your solvers are correct, but how do we convince the others about that? Well, clearly, software testing is not enough. You cannot prove that no bugs are present anymore with software testing. Formal verification, on the other hand, can give us such strong guarantees, but this does not yet scale up with the high complexity of modern solvers. So what seems to be the best way forward in this is by designing certifying algorithms. And a certifying algorithm is an algorithm that does not only solve the problem, but also produces a proof of correctness of the solution. And ideally, this proof also shows that the solution was obtained by correct reasoning. And it's important that this can all be done with minimal overhead in the solving time and without changing the solver's reasoning. And that's because we want to have these highly efficient state-of-the-art solvers to our disposal, but with the extra of having proofs of correctness. So how does this now work? Well, you run a solver on an input problem, and it gives you an answer, but it also gives you a proof of correctness of this answer. And this you give to the proof checker, which goes over the proof line by line and checks if the proof indeed derives the answer for the given input. This is really a success story in STAT. I mean, for many years already, it's compulsory to have proof logging in the STAT competition, and we have many proof logging formats for STAT available. And actually, since the task of checking a proof is much simpler than solving the problem itself, we have formally verified proof checks. But unfortunately, for long, this was still out of reach for other paradigms, like, for example, maximum satisfiability. And that's what I will talk about in the next 45 minutes. So first, I will talk about MaxSAT a bit, introduce it, and how to proof log it, and mostly why hasn't this been done already. Then I will give you an introduction to the VeriPB proof system. And after that, I will start introducing MaxCDCL, but every time I'm introducing a technique, I will show you how to do the proof logging. I will also talk about the literal unlocking that we have seen yesterday in Jordi's talk. And in the end, I will switch a bit to solution improving search by showing how to do proof logging for the encoding of the solution improving constraint using BDD encodings. Okay, so I will talk about clauses, which are disjunctions of literals, about propositional formulas in CNF, like we've been doing already for many times. And I will be using this definition for MaxSAT. So MaxSAT is the optimization variant of the satisfiability problem. And a MaxSAT instance, for me, consists of a propositional formula and an integer linear object. And I will talk about a solution or a feasible solution when I mean an assignment for all variables such that the formula is satisfied. And I will talk about an optimal solution if I have one that minimizes the objective. And I know this is different from many other definitions of MaxSAT, like, for example, the definitions with a set of hard clauses and soft clauses, but actually they are equivalent. So we'll use this definition, but all the work can also be used when you're thinking about hard and soft clauses. So why don't we have some proofs? Well, what has been done in designing proof systems for MaxSAT so far? Well, mainly proof systems have been studied to theoretically study proof complexity. There are a few solvers that are specifically created for creating proofs in one of these proof systems, but they do just not compete with state-of-the-art MaxSAT solvers. So up until now, we don't have any certified state-of-the-art MaxSAT solver using some native proof system for MaxSAT. And to have an idea why that's the case, well, let's take a look at what kind of MaxSAT solvers there are out there in the world. We have four main different categories of MaxSAT solvers. And they all use very different reasoning techniques. So to have a good native proof system for MaxSAT, it needs to understand all of these different reasoning techniques. And that's not so easy to come up with a proof system that's able to do so. And if you think about SAT, where proof logging is very mature already, well, most of the state-of-the-art SAT solvers use CDCL-like solving. So they use kind of the same solving scheme with a lot of optimizations, of course, which are not that trivial. But of course, this is really a different ways of approaching solving a MaxSAT instance. So that's probably the main reason why we don't have a good native proof system for MaxSAT. So let's think out of the box. How can we proof log MaxSAT solvers without a native proof system? And the first idea would be to just use one of these proof systems for SAT. But there is not such a thing as an objective in SAT. So how can we even reason about optimality in these proof systems? Another idea, that's an idea that we have received quite a lot already from reviewers when we published one of our papers on proof logging MaxSAT with VeriPB. And it goes as follows. Why don't you use some state-of-the-art MaxSAT solver without taking into account proof logging for now? Check if this solution is actually a satisfying assignment. Then create a formula, f prime, that says f needs to be satisfied. And I have a strictly better solution. And then run a SAT solver with standard proof logging to actually get certificates of unsatisfiability of f prime, saying there is no such thing as a better solution. Let's see if this would work. Checking that the solution is a satisfying assignment, that's of course easy to do. But then creating this formula, well, a SAT solver doesn't understand this kind of constraints. So we need to encode it in a CNF formula. And of course, who says that I implement my CNF encoding right? I wouldn't trust myself with that. So that requires proof logging because I need to prove that my encoding is actually implemented correctly. And since proof systems for SAT don't understand this kind of constraints either, well, that's not possible with state-of-the-art proof systems for SAT. But even if you would neglect that for a moment, and let's run the SAT solver. Well, actually, this new call to the SAT solver needs to prove the optimality, which is actually already done in this first MaxSAT solver call. So that causes serious overhead in the solving time. And even if you would not care about that for a moment, then still this approach only proves that the answer is correct, not that the reasoning within the solver is correct. And that's such a pity. So why don't we use a more general proof system? And that's what we do. We use VeriPB as a more general proof system for MaxSAT. It's not designed for MaxSAT proof logging, but we use it for that. So to give you a small overview of what has already happened with VeriPB MaxSAT proof logging, first there was QMaxSAT, which is a solution improving search solver, and the focus there was really on proof logging the Pseudo-Boolean to CNF encodings of the solution improving constraint. And then we had RC2 and CGSS, and we included all of the extra techniques such as stratification and so on to have finally a first state-of-the-art MaxSAT solver with proof logging. And then this year we got back to solution improving search, and we thought, well, we need to have a version with proof logging of the state-of-the-art in solution improving search solvers. So let's do PACOs. And we thought, well, in the end, it's just another encoding of the solution improving constraint, so that's going to be fine. But actually, the reality was different because, well, the dynamic polynomial watchdog encoding, which is one of the encodings that's been used in PACOs, uses some interesting without loss generality. And now this talk will be about branch and bound, which is a third category of MaxSAT solvers to which we are adding proof logging to. And of course, in the end, maybe a little bit about solution improving search. Okay. But first, let me introduce you to VeriPB. VeriPB reasons about the Pseudo-Boolean optimization, about the Pseudo-Boolean constraints, which we are talking about already the whole week. And it does so by using some proof rules. And it's mainly based on the cutting planes proof system, which I will talk about in more detail in the next slide. But it's mainly for example, adding up two constraints. And then we have the reverse unit propagation rule, which is mainly a rule that you can use to derive constraints without actually providing an explicit cutting planes derivation. And you just tell the proof checker, well, here I have a constraint. I know you know an algorithm that can prove that this constraint is indeed entailed. Just do this algorithm and show that it is indeed constrained, that it is indeed entailed. And the algorithm is actually, if you propagate your formula and the negation of your new constraint, and that propagates to a conflict, well, then clearly this constraint is entailed, so it's fine to add it to the formula. That's the idea. We also have the redundance-based strengthening rule, and this is actually a generalization of the red rule in SAT proof logging, where you can do some without loss of generality reasoning. And one of the examples is to add verification variables, which are variables that are true if and only if some constraint holds. And as long as this variable is never used before in anywhere else in the formula, it's quite fine to see that indeed I can just add this variable. It will not change anything. That it will not change too much in the formula. And that kind of reasoning you can prove with this rule. And finally, we have support for optimization. And you do so by deriving the solution improving constraint, and then prove optimality by contradiction from this constraint. Okay, so I promised you that we will go into a bit more detail about the cutting planes proof system. So we always start from the input formula, and we have literal axioms, which just mean I can derive that any literal can be true or false. We can add up two constraints, and we can multiply a constraint by a natural number. This is just some simple manipulations of linear inequalities, but we also have the division. And that needs probably a little bit more explanation. So if you have this constraint, then you can divide it by a natural number, and you can round up the coefficients and the right-hand side. So to see that you can do this rounding up, well, actually, think about the fact that you can add literal axioms until you can divide this number by C. So that's this rounding up. And then, because we're reasoning with integers, we know that this will be an integer value. So if it's greater than or equal to any number, then it's also greater than or equal to the first integer that's greater than this number that you first had. That's the second rounding. So let's take a look at some example. So we have a constraint, and we can multiply it by 2, where we multiply all of the coefficients and the right-hand side by 2. We have another constraint, we can add it up. Now we can derive the literal axiom that not C is either true or false, which we can again multiply by 2. And then we can add it up. But then something happens. That is because, well, 2Z plus 2 not C can actually be rewritten by 2. Because if Z is true, then I will have value 2 right over here. And if Z is false, then I will have value 2 right over there. So we can divide it to 2, and now we can subtract 2 from both sides. And actually, we have added literal axioms now to remove Z from the constraint. And doing this manipulation, we will call weakening. And then we can divide by 3, and we can round it up. So these kind of derivations we will be using all the time. But what does this now look like in practice? Well, in practice, these proofs are big text files containing lines of derivations. So every constraint gets a constraint ID, and we will denote literal axioms by just literals, which for example, this one is not C. And we denote the negation by the tilde. And then this is just written down as a line of text to the proof. For example, constraint 1 is multiplied by 2, which is the first multiplication. We add constraint 2 to it. We have the literal axiom not c greater than or equal to 0. We multiply it by 2 and we add it up with the rest, and then we divide it by 3. Okay, so you have now an idea about MaxSAT, that we're gonna proof log it with VeriPB, and you have had an introduction on VeriPB. Let's dive into MaxCDCL. And what I will do is I will repeat some parts of the presentation of Jordi yesterday, and then explain how to actually do the proof log. So MaxCDCL, as we have seen yesterday, is a branch and bound solver where you create a search tree for solutions. And every time you find a solution, then you update an upper bound. And then in every node, you check the lower bound of the objective value at the current partial assignment. And if you find that either the current partial assignment is a conflict, so is falsifying a constraint clause, or it's the lower bound is greater than or equal to the upper bound, you have to backtrack. And actually, MaxCDCL extends this by using look ahead with unit propagation and by learning a clause whenever it goes into a conflict, either being it a conflicting clause, so a clause that's been falsified, or when the lower bound is greater than or equal to the upper bound. So what's important is that MaxCDCL knows two kinds of conflicts, namely hard conflicts, whenever a clause is falsified, and soft conflicts, whenever the underestimated lower bound is greater than or equal to the upper bound. But in both cases, MaxCDCL uses conflict analysis to learn a new clause, which is why we can say that MaxCDCL is actually CDCL generalization. So for the proof logging, it's important to see that this part is already done by the people in the SAT community. So we will mainly focus on how to proof log this part. So let me first show you how look ahead works. And the idea is that you already have a current partial assignment, and you want to see if the current partial assignment cannot be extended to a strictly better solution, because then you can learn a clause and backtrack. And this is done by look ahead using some unit propagation, and the idea goes as follows. So you assume that some unassigned objective literal is false and apply unit propagation. And you keep on doing that until either a hard clause is falsified or not yet assigned objective literal is assigned true. And at that moment, you have found a local unsatisfiable core. And I will first show you by looking at the unweighted case. So all of these unsatisfiable cores, these local unsatisfiable cores, will be a disjoint, clause. So every core increases the lower bound by 1. So if we have found enough of these cores, then the lower bound is greater than or equal to the upper bound. And then, therefore, a soft conflict is found. So let's dive into an example. You have an objective and an upper bound of 3, and you have a current partial assignment. So first of all, we assume y1 to be false. This propagates some literals. We assume y2 to be false, which again propagates something. We assume y3 and y4, and this propagates x12, which falsifies some clause in our formula. So that means that given the current partial assignment, assigning y1, y2, y3, and y4 false at the same time gives us a conflict. And by using some conflict analysis, we can see that given this part of the current partial assignment, y1 and y4 cannot be true at the same time. So what we can see is that given x2 and x4 being false, one of y1 and y4 needs to be true. And let's see what happens if we continue doing this procedure and we find 2 more cores. Well, at that moment, we know that given the union of all of these reasons, one of these ones needs to be true, one of these ones needs to be true, and one of these ones needs to be true. So at least 3 literals needs to be true, 3 objective literals. Hence, we find a soft conflict, so we will need to backtrack. And actually, the conflicting clause is the union of the reasons. In weighted MaxCDCL, this works a bit differently. Namely, every local core will get a weight, and the smallest coefficient, which is the smallest coefficient of the objective literals in the core. And every objective literal can now contribute to more cores as long as it doesn't exceed the weight, well, as long as it doesn't exceed its coefficient. So let's quickly look at an example about this as well. So first, let's consider that we have found this local core. Well, then we have y1 and y2 in the core, and actually the minimal weight is 2. So the minimum coefficient is 2, so the weight of this core is also 2. So what we now do is we subtract the weight of the core from the coefficients of its literals. And then y2 gets coefficient 0, so we cannot use it again. Next, we find a new core with y1 and y5, and we do exactly the same again. We have weight 1 of this core, so we subtract 1 from both objective literals in the core. And then we find a new core with y1, y6, and y8. Cannot be true at the same time, cannot be false at the same time. So we do the same thing, but now we see that we have enough with these two cores. So the idea is that given the union of the reasons of these cores, so given the current partial assignment, the lower bound is greater than or equal to the upper bound. So we will not find a better solution in this current partial assignment. So we want to backtrack.
Just a observation or comment or question, I guess, to check if I'm following, but this difference is that you only do this with unit propagation, of course, but if we ignore this is essentially just core guided search with OLL rewriting, right? But at a particular point in the search tree.
But right after doing this look ahead, you just reset the objective.
Yeah.
So this rewriting is just for weighted core extraction.
It's a mental rewrite.
It's comparable to weighted core extraction.
Yeah. But I think it's exactly the OLL algorithm, but sort of just in a local part. And then afterwards, you will throw away the information. You will also you don't sort of keep a rewritten objective or anything, but the way you're sort of deciding whether you can use a literal again or not is exactly the same.
Yeah, except for the fact that you don't create verification variables.
Sure. Yes. Yeah. Sure.
So the conflicting clause here will be the reason of this soft conflict. Okay, so how can we now proof log this? Well, what we want to derive is this conflicting clause, because that doesn't exist in the solver. We want to derive it. And how can we do that? Well, we'll start from the found disjoint clause. And we can write it as a pseudo-Boolean constraint. Take, for example, the first one. So given that x2 and x4 is false, y1 or y2 needs to be true. Well, if x2 and x4 is false, then y1 or y2 needs to be true to satisfy this pseudo-Boolean constraint. And these are up due to the way they are found by look ahead and by unit propagation and by conflict analysis. So what we will do in the derivation is we'll multiply these constraints by their weight, and we'll add them up. And we get this constraint. If you look well, here you already see somehow the clause that we want to find this appearing. Okay, but I told you by the optimization support of VeriPB, we can always derive a model improving constraint, saying I'm searching for a strictly better solution, and if I can prove optimality, then I will be able to prove a contradiction from that. But we can use now this model improving constraint. And I will write it now in normalized form, because typically in the VeriPB proof checker presents mostly in normalized form. And what I will do is I will weaken, so I will add literal axioms such that this part coincides with this part, except then that the negation is, that the sign of the literals is different. And if you see what is happening here, this 13 is actually the sum of these coefficients. So let's add them up. What happens now is that 5 by 1 plus 5 not by 1 will actually be 5, right? So what I can do is I can rewrite it by 5 and I do that for all of the literals, which then can be rewritten to 13, and I can remove this 13 then from both sides. And then I only have this. So this part greater than or equal to 2. So let me divide by a very large number, by 100, and round up. Well, indeed, then I have my conflicting clause. So that's the derivation. So that's what we do whenever a soft conflict is found. We write this derivation to the proof file, and the conflicting clause can be proven. So after that, on this conflicting clause, MaxCDCL runs conflict analysis and to find an actual clause that will be learned. And this clause is again reverse unit propagatable. So whenever MaxCDCL finds optimality, that happens when MaxCDCL derives a conflict at decision level 0. And actually, it turns out that similar to CDCL, when it finds unsatisfiability, you can prove this by reverse unit propagation of the contradiction. Okay, so that was standard bench and bound already. Well, standard MaxCDCL. Let's look into literal unlock. And remember from yesterday that the idea of literal unlocking is that you don't search for clauses as local cores, but you actually search for disjoint cardinality constraints. Let's take a look at an example. So suppose you have found the following disjoint cores. So you have found, given the current partial assignment, y1, y3, y5, and y8 needs to be greater than or equal to 3. And given the current partial assignment, y2 plus y4 plus y6 needs to be greater than or equal to 2. So by adding them up, you can see, since they are disjoint, that y1 up until y8 needs to be greater than or equal to 5, which is a lower bound. And in this case, the upper bound was 4, so we have found a soft conflict. That's the idea. How can MaxCDCL find these cores as being cardinality constraints? Well, it does actually the same as it always does. It starts, okay, sorry. Let me first make my life a bit simpler, and let me remove the reasons, because that will not change anything in the derivations. That will not change anything in the exploration. That will just be carried around all the time.
So you're not removing it. We're ignoring them for now. They're somewhere, but we're not focusing on them.
No, we're just ignoring them. So what will be done first is MaxCDCL assumes a not yet assigned objective literal false, and that propagates y1 and y3 to be true. But if you look good at the first core, then you can see that actually this core is already satisfied. So at this moment, we say that y9 unlocks core 1 on y3. And from then on, MaxCDCL says, okay, but I can now use y5 and y6 in my search for a new core, because it's actually, if I would assign y5 or y6 true, then actually I would have already been able to increase my lower bound. So let's assume them false. So we'll assume y5 false, we'll assume y6 to be false, and this propagates y7. But now this constraint is satisfied as well. So again, we can do the same. We can say that y9, y5, and y6 unlocks my second core on y1 and y7. And the same thing happens. I can now start using y2 and y4 and y8 and assume them false in my search for a new core. So whenever I now assume y2 to be false, I get a new core. Namely, this one. y9, y5, y6, and y2 cannot be true at the same time, given the current partial assignment, which we ignore for this moment. So MaxCDCL now says, okay, I can conclude that y1 up to y9 needs to be greater than or equal to 4. Is that actually true? Well, let's think about it. What if y9 would be true? Well, then clearly we have 1 of the first one, 2 of the second one, and y9 is true. So indeed, we have a lower bound of 4. So let's assume y9 is false. Then y3 is propagated. So what do we have with the values of y5 and y6? If at least one of them is true, indeed we have a lower bound of 4. So let's assume them false. Well, then y7 is propagated, but actually also because of this new core, y2 is propagated. So we have a lower bound of 4 also when I use these assumptions of putting them all false. So I'm 100%, well, based on this case splitting argument, I know that my lower bound needs to be at least 4 at this moment. That's the idea. Yeah. So how can we now do the proof logging for this? Well, first of all, what we will first derive is constraints that actually mimic this propagation. So for example, if we look at the unlocking of my second core, I will add the constraint saying that if y9, y5, and y6 are false, then y1 and y7 is propagated. And for all these propagations in the unlocking, I will add such a constraint. So what I will have to derive from these constraints is this constraint. But first, let me quickly introduce some extra notation. So I will say that the set L, big L, is the set of new literals that were not used in the previous course, but that I will use in the newly derived core. And for every core, I will divide the literals in this core by 2 sets. One set, the U set, is the one that has the literals that were propagated through. And the R set, the rest set, let's say, is the set of literals that are assigned false in our search. So we say that L unlocks core 1 on U1, and L together with R1 unlocks core 2 on U2. So the constraints that we actually get are of this form. So L plus the rest of the cores that were unlocked before together propagate the literals in U of the core that I'm looking at, that I'm unlocking at this moment. So what I will need to derive is that L plus the literals in all my cores that I have been that I have found that I've unlocked before are greater than or equal to the sum of the right-hand side of these cores plus 1. So I have an increase of the lower bound of plus 1. Now, let me make that a bit more formal. So what I have is I have the constraints Li greater than or equal to Bi, which is just the different local cores, and the I is in increasing order of the time the cores got unlocked. So for every core I that gets unlocked, I can say that L plus Rj with j smaller than I, so all of the rest literals of the cores previously unlocked, propagates literal L in Ui. And finally, I have the final found core, so this new core, that is L plus all of the rest literals cannot be true, cannot be false at the same time. And from that, how we will prove this is by induction, we will derive this constraint. And actually what it says is if my literals in L, so my new literals, together with the literals that were the rest literals that were not assigned to in the previous course are false, then I have an increase of lower bound plus 1, which is actually the reasoning that I did right here. So if all of my literals, y9, the new ones, and y5 and y6, the ones that were in the unlocked course before, are false, then I have an increase of the lower bound plus 1 by y1, y7, and y2. That's the idea. So to derive that, we do this by induction. And for the base case, it's just a new core that we have found. And then for the induction step, we show that there is a cutting planes derivation, and I will not have the time to go completely into it. If you have interest in that, I can show it later on. I have some backup slides on this. But I show that I can derive this from the induction hypothesis. And in the end, when we reach I equals 1, then we have indeed derived a new lower bound. Okay. So that's everything about the Benjamin bound solving in MaxCDCL. Let's turn into the BDD encoding. So the idea is that MaxCDCL actually combines Benjamin bound solving and solution improving search, sometimes whenever it seems handy based on a heuristic to also encode the solution improving constraint using some BDDs. And the idea of this BDD encoding is that it will introduce some diagram, some decision diagram, where every node corresponds to a part of the original Pseudo-Boolean constraint, and every node propagates based on one decision list. So if you look at the first one, what you want to do is our objective needs to be smaller than or equal to 6, and our objective is 3x1 plus 4x2 plus 5x3. Well, if x1 is true, then this constraint needs to hold. And if x1 is false, then the other one needs to hold. And so for every node, we'll add some variable, and thus if the false node is propagated through, then the constraint in the root is falsified. So how is this now encoded in clauses? Like I just said, for every node, it will introduce a new variable with meaning that the constraint in this node is true. But actually, if you look well enough at this constraint, well, if 4x2 plus 5x3 is smaller than or equal to 6, it's also smaller than or equal to 7, right? Because if both of them are true, then you get a 9. And if one of them is true, then you get 5 or 4. So smaller than or equal to 6, but also smaller than or equal to 7. And actually, we will represent this by an interval. So this means that B is true if and only if the constraint with the right-hand side 5, 6, 7, or 8. That's how we will present it. And then after introducing these variables, clauses are added to the solver to actually mimic this propagation. For example, if you look at this clause, this says that if this node is false and x1 is true, well, then that node needs to be false as well. And these clauses actually encode the meaning of, encode the solution improving constraint in the CNF program. Okay, so how do we now prove on this? Well, we want to have V2 actually reified by some constraint with some interval at the right-hand side. That's not really possible, right? That's not a Pseudo-Boolean constraint. So what we do is we'll have different right-hand sides for the reification in both directions. And reification we can easily do by using the redundance-based strengthening rule, but this is not really a reification. This is some weird reification with some weird numbers in the right-hand side. So we need to do a trick to be able to do this. What we'll do is we'll introduce a V variable, which means the constraint with the lower bound in the interval. And we'll introduce a new variable, V prime, which is only known in the proof. It's never known in the solver, which is true if and only if the constraint is true with the upper bound. And then if we can prove that V prime implies V, then we can prove that this implies V prime and V prime implies V. So this implies V. That's how we will prove this. And then in the second step, we will derive the clauses. I will not go into detail about that because that's actually quite a straightforward cutting planes derivation using the definition that we will be deriving. What I will need is proof by contradiction, and that's possible to do with redundance-based strengthening. If you want, I can later show you in a bit more detail how it works, but for now, let's just assume that I can do proof by contradiction by doing a trick with the redundance-based strengthening rule. Okay, so how can I now prove this? Well, if I have the reification of my V and V prime, and I can prove that if x2 is true, then V prime implies V, and if x2 is false, then V prime implies V, well, then clearly I can also derive that V prime implies V, right? So let me show you how to derive one of these two constraints. And let me show that if x2 is true, then V prime implies V. So what we have is for V22, which is this node, I have V and V prime variables. And for node V3, which is this child, I have the actual reification that I already want. Because we start deriving the reification bottom to top. Let's do this by contradiction. So what I can assume now is that x2 is true, V prime is true, and V is false. And I already have these constraints derived. So what I can do is, from the fact that V prime is assumed true in my proof by contradiction, I can use the definition. And from that I can derive that 4x2 plus 5x3 is smaller than or equal to 8. And I also have assumed that x2 is true. So using that, so adding it up, but after multiplying it by 4, I get 5x3 smaller than or equal to 4. And then using the definition of V3, so plugging it in, I can now derive that V3 is true. On the other hand, from the fact that V is assumed to be false, I can use the definition here to also know that this is false. Hence, 4x2 plus 5x3 is greater than or equal to 5 plus 1. And if I just add literal axioms to weaken x2, so to remove x2 from that constraint, I get 5x3 greater than or equal to 2. Well, this one is false, so that means this one is false as well. So I derived, using the definition of V3, that V3 is false as well. But that's in contradiction with this one. So indeed, we have found a contradiction. So I have proven that if x2 is true, then V prime implies V. And the same reasoning happens for the constraint where you want to derive that what happens if x2 is false. So indeed, I was able that way to derive the reification of my V variable, and now the clauses can be derived from these reification constraints. And actually, in MaxCDCL, it uses actually MDDs, which means that if you have some at most one constraint saying that at most, for example, this node x3 or x4 can be true, but not both of them at the same time, you can actually split on x3 is true, x4 is true, or none of them are true. That's what is used in MaxCDCL, and actually the derivations that I have just shown you can be generalized to the case in MDDs. So to wrap up, in future work, we are currently working on the implementation. That's work that I've been doing with Jordi a lot lately. This is still work in progress. On the other hand, this is a third category of MaxSAT solvers where proof logging has been adding to. So it would be nice to have all 4 different categories. So the next one would be nice to also have implicit hitting set solvers. So in this talk, we have shown how to add proof logging to another MaxSAT solver, namely MaxCDCL, which is a branch and bound solver. And we have shown that pseudo-Boolean reasoning really helps to express these MaxSAT algorithms. So proof logging for MaxSAT is possible with VeriPB. And that is, I think, one of the main takeaways here. So that's it. Thank you for your attention.
Thank you so much, Dieter. Questions? So I have a question. So how far are we from like actually seeing how this works in practice?
We currently have an implementation of the basis. So up until here, with the class learning, that we have implemented, but we don't have done experiments on that yet. That's on my to-do list for the next weeks. And then the other things, we're currently doing the MDD encoding. We're quite close, I think, to have that as well, but yeah, not finished yet. And then after that will be the literal unlocking. Also needs to be done.
So you're saying, yeah, so the fact that that you know what the cutting planes derivations look like, you still have to put this into code and actually generate it and get it to work and deal with all off by one indexing errors.
Yes.
And I don't know if this is the question to Dieter or to Jordi, but given that you have this now, sort of this shows that behind the scenes, this seems to be a pseudo-Boolean solver in some sense, right? So, or at least, like,
Yes,
could you lift it? Have you thought about maybe doing a pseudo-Boolean version?
I think it makes sense. Yes, totally. Indeed. Well, I think that the same comment applies to most MaxSAT solver, in fact. No, but yes, indeed, it makes sense. I think that would be nice.
So one other comment, I don't know if you had this is somewhat related to some other discussions we've had also. I think where you had this example where you did this weighted course and you computed the core weights 1, 2, 3. Could you maybe go back to that slide? Because I think that this is somewhat too. I mean, I understand this is not
this one.
We were getting some weights for the course also. It was a weighted example. Yeah. Yes. So see if I can explain this well. So there's a paper that I think is interesting and that maybe, or that I have not read it well, so I do not know it well. So when I say I think this deserves to be, known more widely, that's at least by me. So one interesting view on this is that I think is due to George Katserelos is you can look at the course and think of your objective now as just a linear function. I mean, I guess it is a linear function now, and look at the course. What you're actually using is you're computing a solution to the dual, not necessarily an optimal solution to the dual, but these weights are sort of working in the dual, and this will sort of be some kind of Farkas certificate, if you wish. And it holds in general for, you can view core guided search like the lower bound that core guided search computes based on the cores that it has found right now. Those cores are chosen in such a way that the core weights will actually be an optimal solution to the dual. So this is a George Katserelos paper from I think SAT 2023. It's just because note that you were sort of taking the weights. The thing you're doing when you're looking at the coefficients and then decreasing, the whole point that you want to do is you want to make sure that these multipliers are such that when you sum up all of the constraints, you get an expression that is a lower bound on the objective, which is exactly what like the dual will give you. So yeah, I don't know. But then the very interesting thing, the one thing that I think is very interesting is this unlocking idea, which is somehow, if you try to express it in a core guided language with OLL rewriting, you can say, okay, you're making some, you already decided that I've already canceled the literal in the objective, and so I won't make any more assumptions on it. But then somehow in a very structured way, you detect that, oh, when I made some other assumptions, this guy propagated anyway. And then you sort of say, okay, maybe actually I will try to use it then anyway. I mean, I think it would be an interesting question if you could take this literal unlocking and think about like what would OLL by OLL style core guided search with literal unlocking look like? Would this be like a good idea? Because it's an intriguing idea, this unlocking business. So. Other questions, comments?
Could you go to the slide where you derive y prime and y, or the other way around? This y to comma 2.
Are you talking about the MDDs or the BDDs?
Yeah.
Okay. Is it this one?
Yes. And there you use the step that you use this V3 at some point.
In the proof by contradiction.
Yes. And this V3 is in a lower level, and this pattern would emerge into a recursive call,
Yes.
Right? And I think you can just add the reification constraints of V prime and V. One, the right implication, this reification, from the other, the left implication.
Yes.
And if you add
yes.
them, you cancel the coefficients, and then you don't have this recursive call, but just one addition and one division. One addition of the two, and then dividing by the right coefficient, and then you get the constraint you want, that the one implies the other.
How would you do this?
So you want to derive that prime implies non-prime. And then I'm using the reification of prime implies 4x2 plus 5x3 less than equal to 8, which is written down as the negation of 3 prime plus 4x2 plus 5x3 less than equal to 8. And from the other, I take the other direction, the reification from that. There is v plus 4 times the negation of x2 plus 5 times the negation of x3 less than equal to 5. And if I add those two up, then the x2 and x3 cancel each other out. And then I still have enough on the right-hand side. Oh, I forgot. For the v without the prime, there the right-hand side gets larger because we add this big M, which is all the coefficients added up. So it's 4 plus 5, which is 9. 9
so it's greater than or equal to 1.
You can also think about, I don't know, I feel like I'm not able to do this online right now, but if you just suppose you have two-way reification for both and you try to wrap, like one other thing that I wonder if it happens if these two constraints start ping-ponging and propagating things. I mean, maybe something can be.
Test that.
Maybe an offline discussion,
Yeah.
but interesting. More comments, questions? Okay, so then let's thank Dieter again.